So we're almost done this unit. This is our third lecture on magnetic force. It's magnetic force on a current carrying conductor. It's section 8.3 from your textbook. And we talked about magnetic force for a single charged particle. If we have a conductor with many charged particles kind of moving through, so a current carrying conductor, a wire would be the most common example. The magnetic force is calculated in a way that is similar to the way we were doing it previously, with just a magnetic force of a charge. But now we have to consider both the current and the length of the conductor. So we're going to focus on just straight line conductors. When you cover physics in university, you'll start to see other types of conductors, but that goes beyond the scope of this course. Now, the right-hand rule for a current carrying conductor is important to remember as well. When we talk about the right-hand rule for a current carrying conductor and we're talking about magnetic force, our thumb represents the current, our index finger represents the magnetic field, and our palm or our middle finger represents the force going upwards. And we will look at this image here. We have our charges going to the right, and we have our magnetic field that's directed into the page. So let's figure out where our force would go. I'm going to just quickly switch to our video capture here. Let me go back to this image. So red, I was using red for the thumb or the velocity. And in this case, it's the direction of the current. The blue is going to be the magnetic field, and it's going into the page. So I'm going to have to move it like this. Our force would be directed up. So this current carrying conductor would be experiencing a force pushing it up. And on that page, you can kind of do this as well. If you kind of imagine putting your thumb pointing to the left and point your index finger at the screen where the conductor is, your middle finger can only point up. So I'd like to copy this down. The magnitude of the current times the length of the conductor times the strength of the magnetic field times the angle or sine of the angle between I and B. That gives us our magnetic force. So it's not too difficult of an equation. We'll look at this conductor that is 45.2 centimeters long, and it's going through, or it has a current of 12 amps running through it. The magnetic field is 0.3 Tesla, and we're going to tilt it, and we'll see what happens at different values of theta. So 0, 45, and 90. So let's first write down the equation. It's FM equals, not Q, but I in this case, L, B sine theta. And these values are all going to be the same. The only one that's going to change is the sine theta. So I'll substitute the I in, which is 12, the L, which is 0.4, was it 45? 452. So 45.2 centimeters. My Tesla was 0.3. And then I'll write sine theta. Now when this is 0, so for different values here, this is when theta equals 0, FM will equal 0. When theta equals 45 degrees, FM is going to be this value, 12 times 0.452 times 0.3 times sine of 45. And I have to limit this to just two. I'm not going to use the calculator this time. There's two significant digits, so it'll end up as 1.2 newtons. And when we are at a 90-degree angle, we'll have sine of 90 being 1. So this becomes 1.6. So now we just need to find out what direction we'll be going, whether it's going to be up or down. So looking back at this image here, I'm going to the right. The component of my magnetic field is directed upward. So I'm a bit confused here. So let's calculate the magnitude of the electromagnetic force on the wire. So I'm seeing it going in or out of the page. So let me just see here. I don't know if that up that they have there is correct. Let's just quickly go back here and I'll show you what I mean. So this is how it would look. We're going to the right with our current carrying conductor. So if there was this pen, it would be going to the right. The magnetic field, the component that's affecting it is to the north, up. So that would push this up towards us. So I'm going to put out of the page. I'm not sure why that answer is like that for that question, but we'll just keep that in mind. Try to fix that next time. Here's another question. We have two electric poles that are supporting a current carrying wire. The mass of the 2.5 meter segment of wire is 0.44 kilograms. We have a 15 amp current that travels through the wire. The conventional current is oriented due east, horizontal to the Earth's atmosphere or surface. And we have a 57 microtesla magnetic field at this point, and it's oriented to the north. So let's figure out what our magnetic force will look like. And it's going to be using the same equation, Fm equals ILB sine theta. Now one of these, my current is flowing east, and my magnetic field is directed north. So because that's a 90 degree, I'm just going to opt not to write the sine theta or sine 90 degrees at this point. My current flow is 15. It's a 2.5 meter segment. My Tesla is 57 times 10 to the negative 6, because it's micro Tesla. And if I multiply these together, I end up with, I'll just not show the calculation because I don't have that ready. It's 2.5 times 15 times 57, and that's going to be, after I round, it's going to be two significant digits, so 2.1 times 10 to the negative 3 newtons. I now have to figure that my red is going to be my current, and I have that traveling to the east, so I'll use right as the east. My magnetic field is going to the north. So if this is east and this is north, then I'll be moving up. So it's not in the page at this point, because physically in the world we would be going, the wire is going to be either directed up or down, or it's going to have a force going up or down. Let me put the next part of this question. It says we have to figure out the gravitational force that affects this 2.5 meter segment of wire. So we know the mass of the wire. It is, force is going to be mg, and the mass of this wire is 0.44. G is 9.8. So when we multiply those two together and we round, we end up with 4.3 newtons. That's going to be directed down. So the net force oh, we don't have that coming up here, but the net force is actually going to be um, very close to 4.3 newtons down. If we round for significant digits, it'll be the same. So that's why we don't notice that effect. But there is this effect of the gravitational field of the Earth kind of pulling up on that current carrying conductor, that wire. Here's an application for loudspeakers. What we actually have is a solenoid that when we run electric current through that solenoid, it actually pushes the magnetic core in and out. And by doing that, it creates vibrations in the air waves, and those vibrations in the air waves create sound that we can hear. So this is an application of a magnetic force on a current carrying conductor. Another application is an electromagnetic pump. So these are pumps that basically to pump blood through a person who's on a dialysis machine. What they use is actually an electromagnetic pump because it applies less pressure on the body, and it uses this magnetic force to kind of pull or push the charged particles in the blood and get them moving.